It's called Understanding the Linux Kernel. It's very theoretical, so there's not a lot of projects going on in the book. So it just tells you how the kernel is structured and how it works, basically. There are books on how you can dev a kernel, and there's a lot of resources on the YouTubes about how that could be done. So I chose this route. The first one is just introductory. Tells you about the file types. Everything basically is a folder or directory, whichever you want to call it, the Linux system. So let's say files. Do files. All you get is a folder, right? So you can go to any one of these folders, and it's a folder because it's something that it's just for human beings to be able to view and understand it. So for the human to understand, it has to be human consumable. So there are different types of file type. So you have a regular file, the folder or directory, symbolic links. These are just links to another folder or file. And you have the block-oriented device file, character-oriented device file, a pipe and name pipe file type, and then you have a socket. I used to think a socket is something. I thought that a socket had a relationship with the NIC, the network interface card, but then this is just the way two processes communicate if they intend to communicate with each other. And then you have a file descriptor and an inode. Basically, from this chapter, an inode is just a data structure. It holds information about a file, right? So and this is needed by the file system itself. So imagine you have a file and you want to open it. It has to have this thing called an inode, and the and this inode has to be provided to the file system. And in the file system, you have to have like the file type, the length of the file in bytes, a device ID. So probably where it's stored. Is it stored in RAM currently, or is it stored in like a HDD, right? You have to have the inode, supply the inode to the file system, UID of the file owner, user group ID of the file, who can, if I own the file, am I allowing everybody else to be able to view the file, and if so, who, and what access rights do they have? And you get like when the file was last changed or updated, and then you have the access rights and the file mode of the file. So access rights are basically rights that you're granting to people, right? So you have the owner, with the person who created and owns the file. Then you have other people who use it, and there are other people who can see it, right? As the owner, you can read, write, and execute a file if the file is an executable. As a user in a group, a user of a file in a group, there are privileges that you can have, or access rights that you can have. You may be able to read, write, and execute a file if a file is executable, or the owner might say, well, you can only read, write, and not execute the file. Don't know why that will be something to do, but there are And others, you may say, well, you other people, you can only read it and probably execute it, right? So that's how that goes, as it says here. And it has different modes, right? We have like um, we have like this flags, not modes, but flags that we could use for each file, right? So we have the SUID, which sets the user ID. The SGID sets the group ID, and then sticky is a very interesting one. The sticky flag is that, well, let's say you execute a process and that process terminates. You want it to be in memory even though it's executed, and so it's gonna just kind of be probably, I'd say this is something that has to use a lot of main memory. All right, it doesn't use a lot of it, but it's needed so that this things get started up fast, right? So yeah, and then, well, this is where it gets interesting, right? File handling system call. So this file right here, right? This file was opened by me to make use of it, right? So if I decide this is no longer a file I need, like let's say I want to open a new terminal window, right? I can decide to do this like that, and this is a system call that calls the kernel. So right now, anything I do here is in user space, right? This is something you and I can see, but when I do something like an open a file type thing, you want to open a file somewhere, you know, like let's say vim, you want to open vim, if I could spell it, I want to open vim a.out, not a good idea, but well, we can do that, right? You can open a.out, say okay, I want to see the contents of a.out. It's basically a binary file, right? And yeah, you can do that and see what's going on, right? So this is a system call. In order for me to be able to open a.out, I had to send a signal down to the kernel space, where the kernel space is going to be, that signal is like, hey, just open this for me, right? So you had to send it to the kernel space. The kernel space took that system call, and then it produces the a.out file so that I can see it and view it. Now the question is, why did I need to call the kernel? Because the kernel actually sits between myself, the user space, and the hardware. When we open a.out, a.out was actually stored in hardware, right? So it wasn't just somewhere in the ether, it was stored somewhere in hardware. And that hardware, as I told you before, or should I say, everything is stored is visible to us as a file or folder in Linux. So that hardware is actually a partition of our memory, right, or storage device. So yeah, I needed something that will intercede for me if you're a religious person. All right, and the open file usually takes the file path a.out, a read, one of the flags that we talked about, so SUID, SGID, and then sticky, and then you give it a mode. Do you want to read it, write it, whatever, right? So as you can see, the open system call actually returns an open file object, and it returns also file descriptor. The file descriptor is usually an integer, right? I've forgot what the integer is, but it returns an integer, and you can use that integer to actually close the file. Okay, so it says the file descriptor represents an interaction between a process and an open file, while an open file object contains data related to that interaction. So what is going on with the file and all that? Yeah, so if I am sitting at a terminal, right, like they used to do before, sitting at the terminal, and I say, hey, open a.out, right? I'm sitting here and I say open a.out. I am given a special file descriptor, right? It returns a special file descriptor because I might, as the owner of this file, I might be doing something different from someone who's just using it, right? And for concurrency purposes, right? Because people can open the same file from different terminals at the same time, right? You get each a unique FD file descriptor. Creating a file, on the other hand, is not quite. When I create, there wasn't a create file. Actually, there was actually only an open file, right? There's only an open file, and yeah, the reason why is because there isn't really what when you do a create file, you're just doing an open file and you're passing it a path that does not exist, but you want it to exist. So open just creates the file and sets some flags and modes if you want it to, right? So this doesn't really exist, so there is no system call for that. So I won't waste my time. Alright, like I said, when you do a file open, you get a file descriptor. You can take that file descriptor, and every time you open a file, you have to close the file. So you pass the file descriptor, and it looks for that file descriptor, and it closes it. So that is also a system call. Why is it a system call? Because you have to go somewhere and say, hey, okay, this thing has been open, I have to close it and put it back, right? Cool. You can rename a file, and then you have kernel mode. So this is an example, right, of how you can go from the user space, which is this application phase, to the kernel space. So imagine you have two processes, and you only have one processor, right? One core. Now, both this processes come at the same time, but you only have one processor, so that means one has to wait. Now, we have time. Time can also intercede, and now process one wants to read and write a file, right? So we do an open, or maybe just, yeah, we do an open system call, and that system call goes down the kernel mode or kernel space, fetch that document, open and pass it to P1. P1 does what it wants, but as it's doing, the timer ticks and says, hey, the kernel says, hey, I need back whatever control of what is happening, and it passes the scheduler, and it's like, well, there's one that's just idling here. I'm gonna take that CPU, because we only have one, and pass it to process 2. Process 2, on the other hand, wants to only write to a file, maybe to that same file. Pass it to process 2. Process 2 then writes, and then an interrupt happens, maybe an exception or something happens, and then it handles the exception and then pass it back to P2. P2 continues whatever they're doing, and that's how. And these interrupts all happen at the kernel space. So when you go up, you're in the user space where you and I can see and monitor and work with the CPU as we want. Yeah. interesting. uh, Masters and also, these are just process implementation in order for the kernel to manage processes. Each process is represented by a process descriptor, just like a file is represented by a file descriptor that includes information about the current state of the process. All said and done, when the kernel stops the execution of a process, it saves the current state or contents of several processes and their registers in the process descriptor. Because the process descriptor tells a lot, right? Or the FD tells a lot, or PD tells a lot about. PD in this term will be about a process, so a program that's currently running. So in the PD we have the program counter and the stack, and then we have general purpose registers. So I believe that things that the hardware, I believe, registers, right? Like when you're doing assembly, floating point registers, process control registers containing information about the CPU's state, the memory management registers used to keep track of RAM access by the process. So with all this information, if a program halts or maybe gets skipped or whatever, and decides to get back into the kernel to continue work where it picks up it left, the kernel resumes from that particular place. Described to load the CPU registers given the program's counter. That the program counter is basically where did I stop. So in this instructions or instruction set, right, of the assembly, whatever, after you compile it and then it gets translated to assembly, there's a program counter that says, hey, in the C language, you were the last place you were at was basically you're about to print something. So the program counter actually just says that was the last instruction you were at. You're about to start this, right? So continue from there. Now, this is the most confusing. Not confusing. If you read it, you understand it. But it's just not like it just naming convention is just like, man, could be named differently. Reentrant kernel. Reentrant kernel just means you have a lot of processes working in kernel space, right? And they can go out and then come back in. So they just named it reentrant. From that explanation, you may understand it. On the book, it just means several processes can be executing in the kernel space at the same time. Now, these processes, goes without saying that they can, move out of kernel space or have nothing to do there, in which case we just save all these registers, the program counter, and all that, right? So that when they come back in to do something, they remember where they were or what the next instruction should be. So reentrant in that sense, but the name is a little odd. And how do we provide the ability to be reentrant? Reentrancy, we have this thing called they're called the reentrant functions, right? So one way to provide reentrancy is to write functions so that they can modify only local variables and do not alter global variables or data structure, right? And why is this important? Because in the kernel space, you can do a lot of things. In the kernel space, the only thing that is different or private is your stack register. I believe it's only your stack registered as private. All other data, global, variable, are just fully fledgedly given to whatever is in the kernel space, right? So anybody can update, read if and modify a data structure in the kernel space if that is public. So you have to guide that. If not, you'll have race conditions. So we create these functions called reentrant functions that can only they can only play around or modify local variables, so variables that are in their own scope. Um, mm, Address, yeah, so I think this is where it talks about it. I am not sure. Okay, each process runs in its private address space. A process running in the user mode refer or has its own private stack, as you can see. So in the user space, you have your own private stack, data and code areas. On the other hand, process running in the kernel mode refers to kernel data, code areas, and they have their own. Each process running in kernel mode has its own private stack, so you only have the stack, right? Given the kernel is reentrant, several kernel control paths each relate to different processes that may be executed in turn. May be executed in turn. In this case, each kernel control path refers to its own private kernel stack. Several kernel control paths each processes may be executed. Yeah, so you have different kind of like different processes actually working on different paths, right? They be executed in turn, so they could kind of always say, okay, this process and this path, execute this, do that, do this, and so yeah. In the kernel, you have the private kernel stack to yourself. It's indicated here, but every other thing, the code, data, are all just, if they're global, they're just a rundo thing. Now, given that we know that code and data in the kernel space are up for any other process to grab, what do? You synchronize and you take note of critical regions. And critical regions are regions where you have a global variable and in that global variable you send a process to the kernel mode or kernel space, and then now, knowing that the Wild West is in fact and indeed the kernel, you have one process talking to your data that is a global variable. At the same time, you have another couple of processes talking to that same data. Now, if you send the first process in and it sees the value of that global variable to be 1 and it decides to deduct it, then on the other hand, the second process comes in and sees the program counter is 0 and decides to increment it. Now you have two different values for the same variable, and that is a problem. In that case, you get this race condition, right? And this is not what we want. We want to be very, very careful with our global variable, so that our critical regions, so that we make sure that our data stays consistent to all processes that are gonna be modifying, taking a look at that global variable. That's why we take care of synchronization, and that's why synchronization is important. There are different ways to do synchronization, and one of them is kernel preemption disabling. So you can disable preemption in the kernel, and so on and so forth. And that's the theme for today.